First thing I want to point out is there is a steel bridge design handbook that's recently been passed back to the NSBA from the Federal Highway Department. And in that handbook is volume 19. Volume 19 is the corrosion protection chapter. So everything we're going to talk about today is covered here. So I'd highly recommend you go to our website and download that. And you can see the URL there on the screen, aisc.org/SBDH. That will take you to our steel bridge design handbook. Also want to point out that we have a dedicated corrosion protection webpage on our website. So you can see the URL at the top of the screen there, but that talks about all these systems as well and gives some references to some other general resources also. So the first question you might have when you're designing a steel bridge is what corrosion protection system to use. And you can see these are the 5 basic types or the 5 basic systems. There might be a few more than this, but these are by and large the most common. I would argue that even the top 2 or maybe 3 of these 5 are probably more common than others. But all these systems work and they're all appropriate when designing a steel bridge. The question comes as to what use do you have? What's the macro environment you're building your bridge in? What's perhaps even a micro environment that you're going to be building your bridge in? Are some considerations of which choice to go into. I'm not going to get into that decision tree, just going to introduce these systems. But as you can see, the first system we're going to have here is uncoated weathering steel. And I'm not going to steal the thunder of Jennifer and Tom, so I'll let them talk more about that one. Liquid applied coatings is the second one we'll introduce today, otherwise known as paint. The third one is thermal spray coatings, which is also known as metallizing. The fourth one is hot dip galvanizing, which probably most people are familiar with, but we'll touch on that. And then last but not least is A709-50CR. This is a low-grade stainless steel. So I'm going to touch on that. I have one slide on that only, but we're going to touch on that also. So let's get going. First one is uncoated weathering steel. And if you look within the design code or ASTM A709 more specifically, you'll see a summary of various grades. Anything with a W represents weathering steel. And so all these designations are weathering grades. And in a nutshell is what these do is weathering steel develops a patina. So it develops this patina so the outside surface of the steel actually forms a thick barrier protection layer that protects the inner layers of steel. And so again, I know that Tom and Jennifer are going to dig into this a little bit more, and so I don't want to waste time and waste everybody's time again and let them cover this more in depth. But it essentially is what this does is it forms this barrier protection, and it's very common to have these pinholes, but it forms a dark brown color that you can see on the steel itself. But that's normal and that's to be expected, and that's what protects the steel from corrosion protection. I did mention ASTM A709-50CR. This is the low-grade stainless steel. These are some examples you'll see here on some of these pictures. The one thing you'll notice is it's not the stainless steel that you think about for your appliances, okay? The difference between that is the percent chromium that's included in this, in the chemical makeup. So roughly speaking, you have to have 11% chrome to be considered a stainless steel, but it does provide much better corrosion protection than that of weathering steel. Just for reference sake, if you're thinking of your stainless steel appliances, they have upwards of about 30% chrome included in those chemical makeups. So that's what's different. So just don't expect to get a shiny silver bridge when you think of a stainless steel in terms of bridge construction. One of the more common types of systems that we have for steel bridges is modern liquid applied coating systems. So this is paint systems. What we see here on the right here is just a cutaway or a slice, if you will, of a typical corrosion or a typical paint system. We have the steel substrate on the bottom. Usually we use a zinc-rich primer as the first coat. There can be an intermediate coat, which is usually an epoxy coat. And then the top coat is typically a urethane coat. This is just the definition though for a traditional 3-coat paint system. There's many different types of paint systems. There's 2-coat systems. There's even 1-coat systems. So this is just an example of a typical paint system. You can also use an inorganic or organic zinc primer, zinc-rich primer. You can use either one of those. And some have benefits over others. But again, I'm just introducing some of these different systems today. But this is a typical paint system. One thing I want to get past though is sometimes when people think of paint systems, they think of some of these old paint systems. This is an old paint system. All right, this used an old lead system back from pre-1980, and this is not looking good, admittedly. This is not the modern paint systems of today, and I want to get into that just a little bit. Before I do though, this is typically a barrier corrosion protection system. However, the zinc-rich primer does provide some cathodic protection. And these are just some examples of how nice some of the new modern corrosion protection systems, typically or more specifically, the modern paint systems look. Okay, I mentioned these old lead paint systems though. So these were common, back in the 60s and 70s. However, more currently, since like 1990, we've been using modern paint systems. So this is what we need to get in our head when we think of paint systems of today, okay? I believe I have I went too far. My apologies. This is the timeline of some of the new advances in paint systems. And as you can see, pre-1970, lead systems were very common. Well, zinc-rich primers were introduced in the mid-70s. And almost more importantly, from 1980 to 1990, we started to recognize the benefits of surface preparation. And since then, so since about 1990 is when we've started to recognize our modern paint systems. And so I want you to get out of your head this when you think of paint systems, and think more about the newer systems that I showed in the previous slides. One thing we also need to talk about when talking about paint systems are the different thicknesses of coating and how that affects cost. So the table on the left here is our coating thicknesses for various systems. On the bottom, you can see that there's a one coat IOZ system on the left of the. I'm going to go back here just to focus our attention a little bit better. The table on the left here. So this is a coating thickness for a single coat system, a 2-coat polyaspartic, and then a 3-coat systems there. You can see as you add more coats, you add more thickness. That should go without saying. However, when you do that, when you add more coats, you also add more time in the shop that it takes to apply these systems. So just keep that in the back of your mind. Don't necessarily always think that more coats is better. Sometimes that can add more chance for human error, and it also costs more, typically speaking. So just keep that in the back of your mind when you're considering some liquid applied coating systems. So generally speaking, though, as you add more coats, it takes more time and therefore can potentially cost more money. So we highly recommend you reach out to your fabricator when you're considering some paint systems and which one to use. They can give you some good insight into the cost implications of that. I mentioned our typical 3-coat systems. These are what we call our workhorse systems. So whether or not you use an organic zinc or an inorganic zinc primer, this is a typical 3-coat systems. Some of the new systems that are being investigated and being used more and more these days are simply a single coat of IOZ, of an inorganic zinc primer, an IOZ with an acrylic latex top coat, and also some 2-coat systems using organic zinc primer and polyaspartic top coats are some of the more newer systems that are being used these days. Looking at my time here, have about 5 minutes. All right, which we should have plenty of time. We have 2 more systems to get through. The fourth one to mention here is thermal spray coatings, also known as metallizing. This is a combination, when I describe this, is think of a combination of a wire-fed welder and a spray painter. So imagine you take a gun with 2 wire feeds coming into it, and there's an electric current pass between it that melts the steel, if you will, or the actual alloy, and then compressed air blows it on the surface of the steel. The most common types of these are 99% aluminum, 8515, which is 85% zinc, 15% aluminum, which is probably the most common. And then the last one is 99% zinc, which is also relatively common, but I would say 8515 is the most common. But this requires a very angular profile on the substrate because it's requiring on that bond from the alloy itself to the steel surface, and it's hot alloy being applied to a cold substrate. So that angular profile is very important, and the surface itself, surface prep, is very important. These are some examples of what these might look like. As you can gather, they're all relatively gray or silver in color. The one on the top left there is zinc. The one in the bottom is 8515, and the one on the top right is the 99% aluminum. So again, they're typically gray in color when they come out. You have the option to use a sealer or not to use a sealer. Sealers are probably more common than not, but they are an option. So the TSC is typically porous. So sealing can be used to seal that, although there's some discussion that it might not absolutely be necessary. And that's a function of the thickness of the coating system itself. The thicker you go, the less permeable it gets. And there becomes a point when the permeability goes to zero, and therefore you don't really need a sealer anymore. This is a mechanical process, so for the reasons I described, that it's, it's just, you need an angular profile for it because it's the alloy itself bonding to the surface of the steel. Whereas hot dip galvanizing is a metallurgical process. So I'm guessing we've all probably heard of hot dip galvanizing, where we take a piece of steel and we dip it in a hot zinc bath, typically at 830 degrees. The picture on the right there shows that there's varying layers of the zinc itself. And I'm not they're gonna test my Greek here, but essentially I have 100% zinc on the outside, and to your right adjacent to the steel itself is about 90% zinc. So it varies from 100% zinc to 90 as you get closer to the steel itself. It does provide both a barrier protection system as well as cathodic. The cathodic comes from the zinc itself, and the barrier is pretty self-explanatory. It keeps water and salt away from the steel itself, so that's where the barrier characteristics come into play. This is a typical process in a galvanizing shop. Surface preparation is extremely important. Degreasing, pickling, and fluxing is also part of the surface prep process, but it's absolutely required before the steel itself is dipped into the zinc bath. And here's a little bit more on that process. But this is definitely required, that these cleaning solutions of the degreasing, pickling, and fluxing are needed, because anything that's not clean will not grow that zinc coating. So it's definitely an important aspect of the whole process. This is typically governed, I wouldn't say governed, I guess, but the American Galvanizing Association, the AGA, they have a lot more information related to this. So I definitely recommend reaching out to them if you have questions about galvanizing. But galvanizing is a very common use, especially for shorter span bridges where the girders can be dipped into a bath in one dip. That definitely helps from a cost perspective. So very common for shorter span bridges to do this, but all these other systems have their time and place, whether it be uncoated weathering steel, paint systems, metallizing or galvanizing. They all have a time and place. It just depends on what your use is, whether or not you're going to use any one of these systems. So that was a very short introduction to the basics of these, but that's all we wanted to do in this case. And now we want to pass it over to Jennifer McConnell or Tom Murphy. I'm not sure which, probably Jennifer. And then they will take a deeper dive into the manual that they have been working on for uncoated weathering steel. So I believe we're going to hold questions till the end. Is that right, Dr. Barker? We're going to pass it over to Jennifer.
Yes, sir. Yep.
Okay.
Jennifer, go ahead and share your screen and take over.
Okay, thanks. You seeing my slides?
Yep, looks perfect.
All right, great, thanks. Okay, so as Mike said, I'm going to be the first of two remaining presenters for our session today. We're going to transition to talking about ideal uses of uncoated weathering steel. Jeff mentioned we have several options, so we're specifically going to focus on when uncoated weathering steel would be the best choice and what the best detailing, fabrication, construction, et cetera, guidelines are in those situations. So I'm going to start things off and then I'll transition this to Tom Murphy about halfway through. So we're basically going to be talking about this uncoated weathering steel manual that was recently developed and is forthcoming in the near future. So I'll start with some brief background on how this manual was developed. What we'll call the Uncoated Weathering Steel Manual for short, or UWS manual is an even shorter acronym. This was sponsored by the American Institute of Steel Construction and the National Steel Bridge Alliance, with the content being developed by myself and Travis Hopper, Ed Wasserman, and Tom Murphy from Majeski and Masters. As you can see from the high-level outline of the manual that's shown here, the scope of the manual covers the full life cycle of an uncoated weathering steel bridge, from initial design through repair and rehabilitation, the details of which we will be discussing today. To provide some context for why this level of effort was put into a guidance document on this specific material, the answer to that question, like many questions, is really about cost. What we're seeing here is some data that Jeff compiled in 2020 from AISC fabricator members, and this shows the relative cost of different corrosion protection systems. And so what we see here on the far left is the minimal first cost of uncoated weathering steel. There are also life cycle costs, as well as environmental and traffic and worker safety benefits due to avoiding the need for repainting throughout the life cycle. So for these reasons, the recommendation is that uncoated weathering steel should be the default corrosion protection system for steel bridges in environments where its use is appropriate and when it is properly detailed, which will be some of our main discussion points for today. Some final introductory comments before we get into the specific guidance is to talk about some of the objectives of the manual that we had in mind as we were developing this document, which are that first, this document serves as a collection and synthesis of various best practices using the latest available data. This builds off of a Federal Highway Administration technical advisory on the use of uncoated weathering steel that is now about 3 decades old. And the National Steel Bridge Alliance saw a need to provide owners and designers with more information on determining where the use of uncoated weathering steel is appropriate and other best practices. And lastly, the FHWA guidance is in the process of being updated. So the vision for this document is that it will serve as a companion to the FHWA document, which is more narrowly focused on design issues only and does not speak to construction, inspection, maintenance, et cetera at the present. So moving into the more technical content by talking about whether or not uncoated weathering steel is appropriate for a particular site. The overview for this section of the manual is shown here, which is that the main idea of this section of the manual and our corresponding discussion of it today is when to use uncoated weathering steel and when to proceed cautiously with it or not use uncoated weathering steel. The concepts for how to determine this are based on 2 main categories of environments termed the macro environment and the micro environment, which some of the main environments of caution that we will be discussing today are listed here. So to set the background for these recommendations that we're going to get into, many of you may be familiar with the current FHWA guidance on site selection for uncoated weathering steel. Those are listed here, where we can see there are 3 general environments and 2 specific site locations where in the FHWA terminology, UWS should be used with caution. So these are a starting point for whether or not to use uncoated weathering steel. However, what you will notice as you read through this list is that these recommendations are mostly qualitative, and questions like how far from the coast defines a marine environment or how much rainfall is considered high rainfall are ones that are routinely asked. So one of our specific objectives was to compile, review, and synthesize the available information that has been developed over the past 30 years to provide some industry standard guidance on answering these questions where possible. So our guidance on where to use uncoated weathering steel can be summarized by this graphic, which I'll show again in a few minutes, but I'm showing here as a preview for where our discussion is leading. And for now, just emphasize a couple main ideas. First is that we have a somewhat engineered decision tree type process that ultimately results in one of three decisions. Either do not use uncoated weathering steel, or at the other extreme, uncoated weathering steel is ideal, or an intermediate situation that we've termed use uncoated weathering steel thoughtfully. And these intermediate situations are ones where uncoated weathering steel may be the ideal choice. It may perform better or as well as any other structural material or coating system, but also decreased performance of uncoated weathering steel may occur. So in these situations, we recommend adding a sacrificial thickness to the uncoated weathering steel as a corrosion allowance, or developing a proactive maintenance plan and the financial resources to implement it. Or third option would be choosing an alternative corrosion protection system. So we'll walk through the specifics of which environments get sorted into which of these categories. The other main idea I want to emphasize here is that we have two main concepts of macro environment and micro environment, and that a key consideration that's relatively novel in the updated guidance is how these two labels interact to affect the performance of uncoated weathering steel. So to talk more about the concept of macro and micro environment and their interaction, just to make sure everyone is on the same footing with these terms, macro environment is the general environment of a relatively large geographic region. What we're looking at here on the left is a land use map. This one is specific to Texas, but most states have some version of this, and the specifics are not particularly important. What I'd like to highlight instead is that we have urban areas in red, waterways in blue, and various forms of what we would generally lump together as rural in shades of green and orange. The micro environment then refers to zooming in on the specifics of any site within these large geographic areas to consider site features that may lead to a more or less corrosive environment relative to the general surroundings. This typically involves considering what the bridge is crossing and site features like vegetation, which we will get deeper into momentarily. So we'll start with the macro environment considerations, where our main concepts in evaluating the corrosivity of any environment are the presence of chlorides and the humidity, because both of those accelerate corrosion rates. So in short, too much humidity or too much chlorides result in poor performance of uncoated weathering steel and other structural materials. Chlorides can either be naturally occurring chlorides due to the atmospheric chloride concentrations along coastlines, or chlorides from de-icing agents. If we think about the situation shown on the left, where certainly de-icing agents would have been applied by any state transportation agency or any transportation agency, de-icing agents can affect that bridge from two sources, either from leaking joints on the roadway above, which Tom will talk about mitigating in a few minutes, or from being dissolved into the snow melt on the roadway beneath the structure, and then that liquid being dispersed and sprayed onto the bridge from the traffic traveling underneath it. So both of those are considerations we need to keep in mind as we move forward. Historically, macro environments have been divided into four main categories, which are largely qualitative. So if we start to think through these four environments, rural, urban, industrial, and coastal, and think about them in terms of chlorides and humidity, the first conclusion we can make is that the rural environment is relatively benign and there's no special considerations needed here. The concern for an urban environment could be a level of de-icing agent use that is extreme enough to cause accelerated corrosion of uncoated weathering steel. There are no general concerns for an urban environment as a whole, so we will discuss this topic as a microenvironment issue. Industrial environments were a historical concern, but the enactment of clean air standards has mitigated pollution levels to the point where this is no longer a concern. So our discussion of macro environments will focus on defining a coastal environment. As we start to think about defining a coastal environment, we can think about two possible extremes to start to bound our thinking. Perhaps at one end of the extreme, we have the entire state of Florida, which we could argue is surrounded by saltwater. Or at the other end of the spectrum, we have a bridge crossing a body of saltwater. But to think about which of those situations best describes a coastal environment or what the threshold is for the intermediate status, we need to think about the humidity levels and the chlorides. To get more specific, we have two possible definitions of humidity. The first is based on time of wetness, where time of wetness is the number of hours per year that the relative humidity exceeds 80% and the temperature is above freezing. With 60% time of wetness, equaling 5,500 hours per year, being generally accepted as a threshold for concern. And this is labeled as category 5 by the International Standards Organization, or ISO. Steve Chase compiled the data shown here on the right, which shows that category 5 levels of time of wetness are relatively rare, being limited to areas along the Pacific Northwest coastline. Those are the only places we're seeing the red dots representing time of wetness 5. So our recommendations for this level of time of wetness were based on reviewing the performance of uncoated weathering steel bridges that existed in that time of wetness 5 environment. And this was where we started to become the connection between the macro environment and micro environment started to become more apparent. So our recommendations are, in summary, if the microenvironment does not have any features that would further elevate the humidity, and I'll describe what those are momentarily, then uncoated weathering steel is recommended. Conversely, for microenvironments that do cause elevated humidity, uncoated weathering steel is not recommended. So using time of wetness is one metric that correlates with field performance quantitatively, but it doesn't tell the whole story. So a second humidity metric that has been used is simply relative humidity, which is also likely to be more familiar. What we are looking at here is average monthly humidity contour maps that have been compiled by NOAA. And what I want to draw your attention to here are the light and dark shades of red on these maps, which correspond to average relative humidities exceeding 76%. So again, based on looking at field performance data, we see a correlation between when that level of humidity occurs for at least 8 months of the year, or if you want to think about this, in other words, if 8 or more months of the year are in the red, meaning an average relative humidity exceeding 75% for most of the year, we possibly have an excessive level of humidity. From a rough skim of these figures, you can see this generally occurs along a relatively small but important portion along the Gulf coastline. And at these lower humidity levels compared to the time of wetness threshold, significant chlorides are also necessary to be simultaneously present in order to cause accelerated corrosion at levels that may be of concern. What that level of chloride is difficult to precisely determine, but what is easier to analyze is the performance as a function of distance to the coast, which can be indirectly related to chloride concentrations. This is the approach being implemented in the ongoing FHWA study on this topic, but the best available data on this metric at the present time comes from a study by Rich Granata focused on performance in Florida, where 2 miles from the coast was viewed as a reasonable threshold for where uncoated weathering steel could be used with confidence. So this information, combined with the relative humidity data and considering microenvironments, leads to alternative recommendations depending upon whether just one of these parameters, so just distance to the coast is low, but if there's not high humidity, the use of uncoated weathering steel is recommended. Or conversely, if we have high humidity, but we're more than 2 miles from the coast, that also indicates acceptable performance of uncoated weathering steel. But as 2 or 3 of those parameters of coast, high humidity, and the microenvironment start to interact, we become more restrictive on the recommendations on the use of weathering steel. So if only 2 of those parameters are maximized, we recommend that thoughtful use of uncoated weathering steel category. And if all 3 of those parameters are severe, the recommendation is to not use uncoated weathering steel. So now defining what those microenvironments are that are of concern. This is based on the same concept of screening for features that might increase the humidity or increase the chloride exposure. To do this, the considerations are crossing type, vegetation, and shelter from sunlight. Starting with crossing types, we can consider our 3 main crossing types as grade separations, or highway crossings, rail crossings, and water crossings. Then, starting with grade separations, we can further divide this category into whether the bridge is crossing a heavily salted roadway or not. Note the all caps on the word heavily, which I'll elaborate on later, but represents extreme combinations of de-icing agent use and high traffic to cause significant enough levels of chlorides to accumulate on the superstructures of a highway overpass. In the absence of these conditions, and assuming the lack of a coastal environment, we expect to see ideal performance of uncoated weathering steel in highway overpasses. Similarly, because railways are not salted, and the only possible concern here is sulfur oxide emissions, which are at benign levels, we also see good performance of bridges in the microclimate of a railway crossing. For waterway crossings, we have 3 subcategories that we considered. First, most waterway crossings are a benign microenvironment. A more severe microenvironment is when the bridge provides a low clearance over water, which has generally been defined as 8 to 10 feet. The concern here is increased humidity, partially due to the closer proximity of water. And then lastly, the most severe case is a structure over salt water, particularly in a location where there are breaking waves, which in that such situation, the use of weathering steel is not recommended. In addition to what the bridge is crossing, 2 other microclimates to consider are those with dense vegetation and excessive shelter. Dense vegetation can be roughly defined as the vegetation being in contact or nearly in contact with the structure, as this increases the humidity or traps moisture, as shown in the photo on the left, where this girder is experiencing some through thickness section loss in that location. Dense vegetation, like shown on the right, can also cause excessive shelter, which has been roughly defined in some international guidelines as the bridge being in shadow between 9 a.m. and 3 p.m., which we loosely translated to be in shadow for 6 hours per day. In either of these situations, options are to modify the site if possible, or to modify the structure. Getting into some quantification of these microenvironments, whether or not a bridge is heavily salted is largely a function of the snowfall and the average daily traffic, or ADT. Because the largest concern, assuming the joints are properly detailed, as Tom will discuss, is road spray from the traffic below, the vertical underclearance, which is the distance between the superstructure and the roadway, is also important. So we have recommendations for how to define some of these variables, specifically 20 inches of snowfall and 20 feet for vertical clearance, when both of those situations are also combined with a high ADT. This situation has previously been termed a tunnel-like environment, but I'd like to emphasize that the tunnel situation geometry alone is irrelevant if there are not excessive de-icing agents used. So a tunnel situation in Florida is not a microenvironment of concern, for example. Low clearance over waterways is one aspect where FHWA currently provides quantitative guidance of 8 to 10 feet, as previously mentioned, and reviewing literature on this topic leads to the conclusion that that distance is at least acceptable and possibly conservative. So tying all those details together, we return to the flow chart that I showed at the beginning, where the microenvironment and macro environments are quantitatively considered to result in a recommendation on the use of uncoated weathering steel. We can also illustrate that same concept in table form, where the combinations of environments where uncoated weathering steel is not recommended or where the thoughtful use of uncoated weathering steel is recommended are clearly identified. And here I'll note that while those categories occupy most of the space on this table, the vast majority of cases will fall into the all other category for microenvironment and the all other category for microenvironment. So we'll end up in the green square here, resulting in the recommendation to use uncoated weathering steel in most cases. And now I'd like to turn things over to Tom to review the rest of the uncoated weathering steel recommendations.
Okay, thank you, Jennifer. So assuming you've been through the process that Jennifer has just laid out and decided that uncoated weathering steel is the appropriate material for use on your structure, what can you do as a designer or an owner to ensure that you get the best possible lifespan and performance out of that material? So if there's nothing else you remember from this portion of the presentation, it should be this, and that's eliminate joints wherever possible. Its experience is quite clear. Anytime you have water directly discharging onto steel, you have poor performance, whether that steel is painted or uncoated weathering steel. So the use of integral abutment bridges, other types of jointless bridges, semi-integral abutments, moving the joints behind the back walls, using link slabs, anything you can do there to eliminate joints is really the best thing that you can do in terms of extending the lifespan, really, of any kind of bridge, but in particular for uncoated weathering steel. As designers, we tend to focus on the structural aspects of a bridge, but really you need to pay attention to the drainage as well. The drainage systems, where the water goes, really does control in many ways the lifespan of a bridge. You know, in the olden days, they might use open joints without any protection to the steel underneath. We've learned that that's a terrible way of doing things. So if you still have open joints on your bridge, you can do things like install drainage troughs and other things to keep water from getting to your structure. Next slide there. There we go. So once you've done that and eliminated joints as much as possible, and the joints that you do have, you've tried to control the drainage coming off of them, what else do you need to consider? Uncoated weathering steel needs drying cycles to function properly and to form that patina. It's okay if it gets wet as long as it then dries out completely. So if you have trapped debris or dirt, pigeon droppings, anything like that can trap moisture against the surface of your uncoated weathering steel, that will promote continued corrosion and prevent the patina from forming. So here we have a couple of pictures that show examples of this. On the left is a bearing assembly of, I believe, a truss bridge, where you can see that dirt and even mud has gotten in there. And that's going to prevent the water that collects there from ever drying out. You can kind of see in that image that you've already got layers of steel that have begun to peel off there in corrosion. And on the right is an angle formed that has collected debris, and you can see that the dark color of the debris kind of shows that it's collected moisture there, and it's not allowing that moisture to evaporate. And so the steel underneath that debris is continuing to corrode. Areas where this often happens are on haunched girders. If you're not careful with the detailing, these areas will tend to collect debris. So on the left is a uncoated weathering steel bridge that has had a lot of debris collect over the years. I think it's been cleaned off for the inspection in this case, but you can see where it was and the sort of a continuous corrosion that's occurred there. So you need, as a designer, to always think about when you're adding stiffeners and when you're detailing your girders, where debris can collect, where corrosion can be trapped, or where moisture can be trapped and cause corrosion. The image on the right, although it's of a painted bridge, exemplifies one approach to this would be to provide generous clips and copes at the bottom of your stiffeners, in particular in the haunched area, to allow water and debris to not collect. So that was for haunch girders, but of course, even for constant depth girders, you have often stiffeners, transverse stiffeners that are welded on, and these require clips at the bottom to prevent this debris from building up and to allow drainage along the flange length. Many states use a 2-inch clip as their standard. That's sort of a minimal clip size, in our opinion. 3 inches is better. If you can get even larger than that, that's great. One common practice is the pop or the soda can chest. If a soda can pass through it, then it's big enough. And that's a good rule of thumb for any portion of a drainage system design. Next slide. One other approach here is tactical painting of a weathering steel bridge. So painting specific areas where we know are problematic ahead of time is a good way to prevent any sort of future problems with weathering steel. So if you do have joints on your bridge, if you haven't been able to get rid of all of them due to the span lengths or other reasons, then one approach would be to paint the girder just for a short distance either side of the joint. Often states will use a 1.5 times the depth of the girder as a good rule of thumb for how much to paint. That has proven to be very successful. Other areas what might be locally painted are over interior piers, and that's primarily from an aesthetic approach to prevent staining of the pier underneath. There are other approaches that we'll talk about a little later. And then a third region that you should consider painting on an uncoated weathering steel bridge is any area of the girder that might be encased in concrete. So what's being shown here is an integral abutment bridge, and you can see that the area of the steel girder that will eventually be encased when the rest of the back wall is poured has been painted. And that's because concrete is has a very large thermal mass. And so the process goes something like this. At night, everything tends to cool down, including the concrete. And then when the day starts and everything starts to warm up, including the air, and the humidity of the air increases, the concrete still remains relatively cool. Steel being a very excellent thermal conductor in the area of the concrete will also remain cool. So you have warm, humid air against cold steel, and that's what leads to condensation of moisture onto the steel, which then sort of wicks into the area between the steel and the concrete through capillary action. And it doesn't take much moisture over many days before you start to have a problem here with localized corrosion. So that's the reason why you need to paint your weathering steel where it's embedded in concrete. Note that this doesn't apply to top flanges that get embedded in decks. That the issue has never been seen in that region, or at least not to the extent that it's been seen in other areas. Next slide. So we've talked a little bit about water and keeping debris from trapping. Most bridges do have a longitudinal slope to them, and you get water flowing down the tops and sometimes the bottoms of flanges. And that can collect if allowed to sort of deposit itself at bearings in other areas. And so one approach to controlling that is to use drip bars to control the drainage on the flanges, particularly the bottom flanges. There's some debate over the efficacy of this, but I don't think they certainly don't cause any harm. And there is anecdotal information that this does work. So as what's shown on the left here, you have drip bars on the top of the bottom flange, angled at 30 to 45 degrees, and therefore any flow coming down the slope of the flange would be diverted off the edges of the flange. And then underneath, you can just put a drip bar straight across, and that prevents any water flow that's attached itself to the bottom flange from continuing past that point. These are usually welded, especially in areas of compression. If you do have these located on a tension flange, then you're going to want to check the fatigue implications of those sorts of welds. And if it's unacceptable, you can bond them with epoxy rather than welding. Moving into some of the further drainage details, one of the common problems that's been seen in the past are when downspouts from deck scuppers have not been extended far enough below the bottom of steel. And oftentimes a rain event will be accompanied by relatively strong winds, that can blow the drainage that's coming out of the bottom of the downspout back onto the steel and cause an area of continued moisture. And so extending that downspout a sufficient distance below the bottom of steel is important to make sure that doesn't happen. Often a 12-inch distance is used in this area. Box girders are something of a challenge to ensure that they perform adequately. The interior of such closed shapes, either box girders, box columns, anything like that, can collect water. And it can remain wet for long periods of time because there's very little airflow through there to evaporate the water. In the past, there have been many designs that have tried to completely prevent water from entering the girder, and that often has not worked well. So sealing the closed shapes completely against water ingress typically is not successful. And so you need to really think about, should water get in, how do I let it get out so that it doesn't collect? That's not to say that you shouldn't try and prevent water from coming in. Certainly trying to seal holes and being mindful of the gaps at field splices and things like that is still very good, and to try and limit the amount of water coming in. But you shouldn't rely on that as the only method of preventing that. So you need to think about how to get the water out if it gets in. So looking at slopes, again, putting drainage holes at the low points. So that's what's shown on the left here. If you have bottom stiffeners, you might need drainage holes for each stiffener, and then one at the very low point of the cross section. Obviously, you don't want birds and small mammals from getting in your box girder, so you want to screen those, and think about using caulk and other drainage directivity devices there to keep the flow going to the drain holes and not collecting. If you don't do this, water can sit for long periods of time, and it is not uncommon to see closed shapes that haven't been detailed appropriately, having significant corrosion where water has ponded. Next slide. Another concern in design is with dissimilar metals. I like this picture. It's not a design issue so much as it is a construction error, but it dramatically shows the difference when you have metals that really aren't compatible. So what's shown are three nuts on high-strength bolts. The two at the ends were uncoated weathering steel appropriate nuts. The middle nut was a regular steel nut used incorrectly, and you can see that's almost entirely corroded away at this point. So you got to make sure that you have compatible materials. It's easy to kind of go overboard here. There are situations where using metals of different corrosion potentials is fine. You need to think a little bit about area ratios. So if the area of the more corrodable metal is small compared to the area of the less corrodable metal, then that's sort of where you're going to get into trouble. If it's the other way around, then it usually is not a problem at all. And we'll talk a little bit more in the next slide on that. And that happens to be with galvanized components attached to uncoated weathering steel bridges. The weathering action of the weathering steel does drive some corrosion in the attached component. So during the formation of the patina, that will sort of tend to accelerate the deterioration of the zinc coating on the galvanized component, but that tends to stop when the patina fully forms. So if you have areas that are not going to be frequently wet and you expect good and quick patina formation, then attaching galvanized components directly to the weathering steel, it shouldn't be a problem. But if you have more exposed areas where it might take longer for the patina to form, then you're going to lose a lot of your zinc coating, and you should consider electrical isolation between the components with an isolation pad or similar. Next slide. So moving from directly from design considerations into more fabrication and construction considerations, the manual addresses these as well. A lot of the fabrication considerations are more aesthetic than performance. Weathering steel, if it's appropriately fabricated and constructed, can really have quite a pleasing aesthetic appearance. And so a lot of these recommendations that are in the manual are focused on trying to encourage that type of appearance. The formation of the patina takes a significant amount of time. It's not a quick process. And so you want to help that along as much as you can and ensure that it'll be uniform. A lot of the steel, when it comes from the mill, will have mill scale on it. And it will perform well if you leave the mill scale on, but it does tend to cause the weathering steel to have a very mottled appearance during the early stages of the patina, and it really takes a long time before it becomes more uniform. So the recommendation is to shot blast the girders and remove the mill scale so that you get a more uniform patina formation and much improved aesthetics. Any markings that are often used in steel fabrication that are left on the steel and not removed can stain the surface. That's what's being shown in the bottom picture there. And so that's a consideration as well. The other thing to think about in fabrication is material handling. So how the girders are supported in the shop and in the yard, if they have to remain on the yard for a long period of time. Leaving them on wooden blocking for long periods of time can cause localized areas of discoloration. One of the best practices or best recommended practices is if you're going to have your girders in the yard for a while, is to occasionally go out and hose them down and put them through some wet and dry cycles there to start the patina formation process early. Next slide. In terms of construction, the primary consideration here is trying to prevent staining from the girders from staining the concrete piers. There's a couple different ways to do that. Early on, when the patina is just starting, you can get a lot of rusty water coming off the girders. One approach that's shown in the photos here on the right is to wrap the substructure during construction with visqueen or other impermeable wraps to prevent the staining from occurring. The bottom photo shows the sort of a pier that was treated this way during construction and also has a coating system on it. And this is many years after construction. It shows quite well that you can control the staining there. Other approaches are drip pans. These are sort of stainless steel sheet metal pans that are constructed around the bearings to collect the runoff from the girders and direct it away from the concrete surfaces. Concrete coatings are helpful with this as well. And I mentioned before, you can zone paint the steel girders in the area of the pier to try and prevent that from happening. And don't neglect your storage requirements during construction either. There have been instances where girders were stored inappropriately on site, and that caused some difficulty in getting a good patina to form. And in that case, they were allowed to become submerged in floodwaters, which is not a good idea. The next slide. So moving out of construction, and then once the bridge is constructed, the manual provides guidance on appropriate ways to inspect weathering steel bridges, guidance on what the appropriate surfaces should look like. So there's some photos there showing good performing surfaces, and further down below, there's some poor performing surfaces, what to look for as an indication that your patina is not adequately forming. There's something called a tape test that's detailed in there, where you take some packaging tape and apply it to the surface and pull it off, and then the amount and the shape and size of any steel particles that come off, rust particles that come off, will tell you whether the patina is performing correctly or not. Next slide. Moving then from inspection onto maintenance, well, the manual provides some best practices for owners in how to maintain their weathering steel bridges to get the best performance out of them. Issues such as joint sealing should come as no surprise as being a prime recommendation there to keep your joints from leaking water onto your girders. Understanding that your drainage system doesn't function if it's not kept clean, and that they need to be flushed out occasionally. And then girder washing, there's good data that does indicate strongly with a good performing weathering steel. Next slide. So there's a bit of a table here that's included as well, showing what maintenance best practices can be used and are recommended. And so just cleaning off debris with a broom or compressed air is recommended 1 to 2 years, and then washing and flushing your girders 2 to 4 years are sort of the general recommendations. Next slide. The drainage system, we tend to ignore it a little bit in design, and it gets ignored as well a lot of times in maintenance, but often a neglected component of a bridge, but really can have strong impacts on the life of the bridge. So here's a good picture of a drainage system that's no longer functioning. I believe this is inside a box girder, not something you want to occur. So maintenance systems the drainage systems on bridges require regular maintenance and repair to keep them functioning, and shouldn't be neglected. In terms of repair and rehabilitation, the manual has some recommendations as well. So if you are having some trouble with a weathering steel bridge, for whatever reason, they are relatively easy to address. You can tactically paint in the field after the bridge is in place. If you have a joint that's leaking, you can paint the ends of the weathering steel bridge. On the left is a joint and a truss that wasn't performing quite as well, so that localized area was painted to prevent localized corrosion. Next slide. And you can do this for the whole bridge as well. If for whatever reason it's not living up to your expectations, this has been done in the past with no apparent difficulties. This first coat of paint is going to take a lot more paint than it would if it was just a blast surface because of the uneven properties of that. But bridges that have been exposed to the weather for many years have been successfully painted. And the other thing to think about is even if you have to do this at some point, you're still probably ahead of the game in terms of even initial and even life cycle costs, because you've gotten 20 or 30 years of good performance out of your uncoated weathering steel without the need to paint up front. Even if you have to paint later on, in an overall viewpoint, you're still doing quite well. So with that, I think that was the end of the prepared presentation. And so Dr. Parker, we'll turn it over to you and maybe answer any questions that might come up.
There is a question, Tom, in the Q&A. I don't know if you see that anywhere. You might want to.
I can pull that up.
I'm sorry, I was on mute. I was trying to talk, and Jeff realized that I wasn't responding. I want to thank Thomas and Jennifer and Jeff. What I said was I've been a steel bridge engineer for, let's say, well over 30 years, and I learned a lot today. This was very interesting. Now that this report is coming out and becoming public, that's really good stuff you guys presented today. Thank you. We do have a couple questions. Don asked, with the stiffeners clips for drainage between stiffeners, are there any additional measures taken at the bottom flange in order to account for the flange rotation tolerances or an overall deflection and low spot at the midspan where debris or water can collect? And Jeff Carlson did give, I think, part of that answer. He said, regarding the question about overall deflection and low spot at the midspan, typically there is a camber in all steel bridges, and thus the low point is usually at the supports, which is one reason for adding drip bars near the supports. So Tom or Jennifer, if you would like to add to that, that would be great.
Yeah, I think that's a good answer. You know, there are times where you do have a sag vertical curve on a bridge. We try and avoid that just because it's poor aesthetics and for other reasons. But yeah, if you have that case, yeah, you should consider other ways of getting the water off the flange, either drip bars in that case, approaching wherever your low point would be, maybe a drain hole if it makes sense. But you'd have to think a little bit about that if you did have that. It's pretty rare to have a low point along the span.
Okay, thank you. And then that goes along with what Jeff said, so that's good. And then we had one in the Q&A. This is from Pio Miranda. With large box girders painted on the inside, it seems a good idea to open and screen holes for drainage. But what about smaller box girders? For example, for small tide arch bridges where there is no space to fit anyone inside. Should the inside be painted and holes opened as well? Inside paint would probably be damaged by welding process. Painting it after welding would be quite cumbersome. Any ideas?
Yeah, that's a good point. In the manual, we do address where this really shows up frequently are on HSS shapes or very small closed boxes where you can't paint inside. And there the recommendation is you have to think carefully if you're going to try and use uncoated weathering steel for those. And so if you can't seal it, the other approach is to make sure it drains and make sure you don't get water ponding. So plenty of drain holes, appropriately placed drain holes, screen them off. But for small boxes like that, you're right, you're not going to be able to paint them. For larger boxes, we do recommend painting the interiors as another way of avoiding the problem. But smaller closed shapes do pose a problem. In the past, we've tried to seal them completely with varying success, I'd say. So I think providing appropriate drainage is the only way to really deal with that.
Yep. If it's weathering steel, that's a good answer. And of course, the hot dip galvanizers are very proud of their product that they can hot dip inside those HSS or small enclosed shapes to give the cathodic protection inside where you can't inspect it and that type of thing.
Yeah, absolutely. And the manual, I think, recommends using a hot dip galvanized for those sorts of situations.
Okay. Thank you, Tom. Oh, we just had another one come in, and I'm going to read it. I haven't even read it yet. Is there any specific guidance regarding clearance height over roadways referencing speed limits, ADT, etc., specifically regarding weathering steel truss bridges over different roadway types and different clearances?
That sounds like a Jennifer question to me.
Yeah, I'll take a shot at that. I was following along pretty well, preparing an answer until I got to the specifics part. So yes, in general, we think about 20 feet of vertical clearance when combined with high ADT. And for the travel speed aspect, the way I've been thinking about this, if the ADT is high, the travel speed is also simultaneously high. We have very few roadways that have a high ADT, but don't also have a high travel speed. So I think that the high ADT goes hand in hand with a high travel speed, but not necessarily the other way around. We could easily have a bridge on a low volume interstate that has a high travel speed, but not necessarily high ADT. There are some recommendations in the manual specific to truss bridges. Going back to the comments that Tom made about drainage, as long as the members are oriented and detailed in a way that they can have drainage, there shouldn't be any additional concerns, whether it's a truss bridge or a more typical I-girder bridge. I hope that answered all the aspects of the question, but if not, feel free to repeat part of it.
No, that's great, Jennifer. Thank you very much.
Jennifer, I've kind of follow-up question to that real quick. And maybe even more of a clarification. So you said that it's more of a clearance thing in combination with high ADT, correct?
Correct. Yes, absolutely. And high snowfall, you know, in a situation where you're going to be putting down a lot of de-icing agents to begin with.
So it's not to say that you have to be 20 feet clearance period. It's got to be in combination with several other things in order for that to be a true statement, correct?
Yes, that's a good clarification, Jeff. Thanks.
Yeah, okay. Yeah, I just wanted to make sure. Thanks.
All right, with that, we're going to close out today. Hopefully you can see the title slide there. I want to thank Tom and Jennifer and Jeff. Great presentations today that we can implement in our bridge design. On Monday, we're going to bring you 4 really interesting case studies, just case studies of bridges that were built. They're going to be a little short since we got to get 4 of them in 1 hour. But they are really interesting bridges, and well, actually, the last one is a design build project, and how Missouri performed that, which is also very interesting. So, with that, again, my name is Michael Barker. I realize I did not introduce myself in the beginning. I'm the host of this webinar series, along with Dan Snyder, and I want to thank you for joining us synchronously. Keep up with those quizzes. Most of you took them already. So that's great news, and we are working towards that certificate of completion. So we will see you Monday, same Zoom link and same time. Thank you, everybody, and I am going to close us down.